Welcome back again, dear students, for our next session of the chemistry of the inner transition elements. In the previous lecture, based upon the electronic configuration, we have started the very important part, that is the lanthanide contraction and its consequences. So we can continue the same session because we have to cover two more properties. In previous lecture, we have completed this property. So we have the lanthanide contraction and consequences. And consequences. So what consequences we have studied so far? The first one we have studied the basicity. So decreasing the basicity we have studied. So decreasing the basicity is the first of consequences of lanthanide contraction. Second, we have studied the variation in the properties. The properties of lanthanides due to lanthanide contraction. The third consequences we have studied, that's similarity. Similarity in the properties of yttrium and lanthanides. Fourth consequences we have studied, the similarity in properties of zirconium and hafnium. So these are the four consequences we have studied in our previous lecture. Now today we are going to continue this part. The fifth consequences is abnormally high densities of the post-lanthanides. Lanthanide contraction fifth factor is abnormally high densities of the post-lanthanides. Abnormally high densities of what? Of post-lanthanoids. So what is meant by the post-lanthanoids? The elements which are coming after the lanthanides in the periodic table are called as the post-lanthanides. So which are the lanthanides? So atomic number 57 to 71, lanthanum to lutetium. So elements which are coming in periodic table having atomic number 72 onwards are called as the post-lanthanoids. And the elements which are coming before the 57 lanthanum, that is called the pre-lanthanoids. So what is the effect of the densities on the post-lanthanoids? They have the abnormally high density. What is the abnormal? The abnormal means not normal, not per the rules for regulations, or not the normal behavior. Then we can say it is the abnormal. So whenever you are going to the doctor and if you have any type of the indications are there, then doctor says your ovary is not normal, your kidney is not normal, it says. It means they got the abnormality. The same manner here, if the density is much higher than the elements acquired, then we can say they are the abnormally high densities. So this is happening in a post-lanthanoids. In previous lecture we have studied that because lanthanide contraction, we have the zirconium, titanium, zirconium and the hafnium. Vanadium, niobium, tantalum, chromium, molybdenum, tungsten, group 4, group 5, group 6, manganese, technetium, premium. So Citlavisia. So zirconium, because of this lanthanide contraction, what happened? The ionic size of the zirconium is 0.79 and hafnium is 0.78. Niobium has a 0.68, 9 and 0.68. Here it is a 0.62 and 0.62. Here it is 0.46 suppose. 59.59. So lanthanum will be the scandium. Lanthanum, we have the yttrium, and then we have the lanthanum. So we have the scandium, yttrium, and the lanthanum. This is the part. For 21, 39, and 56. This is the group 3, 4, 5, 6, 7. Right. So what happened here, because of the lanthanum contraction here, this ionic file or the 0.88, 11.06 here, and it is somewhat the left to the there. Now, what happened because of the lanthanum contraction, the size of this group 4 onwards, and remember this part. Zirconium and the hafnium have the almost same similar size. Niobium, tantalum have the same similar size. Molybdenum, tungsten have the same similar size, and technetium and the rhenium have the almost same similar size. That's why they are called the chemical keys. So these are the post-lanthanides. These are the pre-lanthanides. The second transition series will be there. So this is the 40. This is the 72, 41, 73, 42, 74, 43, 75. So lanthanides have the similar size, but post-lanthanum also have the similar size. So first transition series, second transition series, third transition series. So second and the third transition series have the same ionic radii. That's why they are called the chemical twins. Now how we calculate the density? Density is equal to mass upon value. Mass upon value. So here the titanium, if we here, zirconium and the hafnium have the similar size, but zirconium is the pre-lanthanum, we can say, and hafnium is the post-lanthanums. So what is the equivalent level of post-lanthanums here, lanthanum contractions? The weight atomic number of the zirconium, it is suppose 40, and atomic number of the hafnium is 72. So it is nearly about double, not exactly double, but nearly double. If it is atomic weight, the zirconium is 91.224, and atomic weight of the hafnium is 178.49. So if you compare the atomic weight with the zirconium and hafnium, is nearly double. That's why as the atomic weight of these post-lanthanides are much higher, nearly double than the atomic number and the atomic weight of the zirconium, the pre-lanthanides, then their density also found to be nearly double. So zirconium has the density is equal to 6.59 gram per cubic centimeter, while that of the hafnium is equal to 13.3 gram per cubic centimeter. That's why the density is also found to be nearly double in case of the post-lanthanum. Same trend also observed in a niobium, tantalum, molybdenum, tungsten, and technetium and the rhenium. That tantalum have the density abnormally higher than the niobium. Tungsten have the density higher than the molybdenum, while the rhenium have the density higher than the technetium. So this is the the effect of the post-lanthanum, that density is much higher than the post-lanthanum. in case of the post lanthanide, and this is because of the only the lanthanum contraction. So this is also the one of the major effect of lanthanum contraction. Now the last effect of the lanthanum contraction is 6. Is noble character of the post lanthanons. Noble character of post lanthanons. Now, because of the lanthanum contraction here, the reactivity of the post lanthanons is found to be decreases compared to the pre-lanthanons. Let's take the example of osmium, iridium, platinum, and then we have the gold, and then mercury. So osmium 76, iridium 77, 78, 79, 80 atomic number. While if you come to the previous period here, we have the ruthenium, rhodium, palladium, silver, and you have the cadmium. So 48, 47, 46, 45, and the 50. So these are the elements from the second transition series which are this called the pre-lanthanides. These are the elements from third transition series which are called the post-lanthanides. So reactivity, because of lanthanum contraction, the reactivity of the post-lanthanum is found to be decreased than the elements which are come before in the same group, that is commoners. In the same group are their commoners. So osmium is found to be less reactive than the ruthenium. Iridium is found to be the less reactive than the rhodium. Platinum is found to be less reactive than the palladium. Gold and is less reactive than the silver, and mercury is the less reactive than the cadmium. So this is also one of the effect of the lanthanum contraction on the post lanthanons. So this covers the entire consequences of the lanthanide contraction. So here the question can be asked that what is the lanthanum contraction, and explain their consequences. Sometimes they can give the specific consequences you have to explain, but sometimes you have to give the any two consequences after the marking system, which are very important, not so less important. So this covers the property. Now we are going to start the next property. So we have to go to study the spectral property. In spectral property, we are going to study two properties. One is the color, and second is the absorption spectrum. Absorption spectrum. So based upon the electronic configuration of the lanthanides, we are going to study these two important properties. One is the first color. Now generally, if you see the color of the lanthanides, it is found that all the tripartite lanthanides can have a striking colors, and the striking colors are mostly in their crystalline state than in aqueous solution. So all the tripartite lanthanides give this striking colors in the crystalline and the aqueous state. Now you observe that these colors were not changed or not affected by changing the anion. If you change the anion, suppose you have taken the NaCl3. If the NaCl3, suppose you replace by the NaBr2, suppose you change the anion, suppose, then it is found that the color is not changed by changing the anion. It is also found that the changed color is not affected by addition of colorless complexing group. Colorless complexing group. So lanthanides have the colors in solid state as well as in aqueous solution. Then you have the question, the colors are not affected by changing the anions, colors are not affected by the addition of the color complexing group, then on what factor the color of the lanthanide depends? The answer is that the color of the lanthanide complexes or lanthanide ions is depend upon, or we can say the color of the lanthanides are its own cations, characteristics of own cations, which cannot be changed by this addition of this color complexing group. And therefore the lanthanides have their colors of their own cations only. So color is exhibited due to the cation patching. Now when the color observed, the color depends upon the which factors? Generally color depends upon the two factors. One is the presence of incompletely filled D or F orbital. The D or F orbital is incompletely filled. That's what this means. That is unpaired D or F electron. If electrons are paired, unpaired, or the D electrons are present, then that comes from the color. Electrons are present in the form of the F orbital, that is 4 electrons are paired, unpaired in the lanthanides, then we can say these are the incompletely filled. And second is the transition of electrons from one cell or one subcell to other subcell. So this is the one of the reason. So one subcell to another. Now the electrons which are responsible for the color property again in lanthanides are the 4F electrons. The 4F electrons for the unpaired, they are deeply buried and they are well protected by the outer line 5S and the 5D orbitals. So lanthanides can have the colors, so they can absorb, this color can be absorbed in a visible region. Absorption of the radiation is taking place in the visible region of the spectra. The combination of this remaining light with white light can impart the colors to the solution. So electromagnetic radiation may pass through this solution, this color can be imparted to the solution when these ions will be get absorbed. So some of the part will be get absorbed. Some of the wavelength we can say absorbed, and the combination of a remaining wavelength with a white light can give the color to the solution. Suppose you have taken the 100% wavelength. Out of that, suppose 80% wavelength is suppose absorbed by the sample solution. What remains for 20%? 20% the remaining wavelength. The combination of the 20% remaining wavelength with the white light can impart the color to the solution. So this is the phenomenon taking place. So this absorption of the radiation is taking place very easily when energy gap is very low. In some cases, if energy gap is less, then the absorption of the radiation taking place very easily. So that is in the visible region of the spectrum. So transition can be possible from one subcell to other subcell. Suppose you have the 4F1 configuration with your cerium 3 plus 4F1 configuration. Lanthanum 3 plus you have the 4F0 configuration. Lutetium 3 plus you have the 4F13 configuration. 4F14 configuration. Right? Ytterbium 3 plus you have the 4F13 configuration. Now, if in case of the lanthanum, transition taking place here, whether it is from subcell or other subcell, then it can show the color property. But sometimes it is possible that the energy gap, energy differences are very larger, then absorption of radiation does not take place in the same subcell. It can take place at the highest subcell, lower to high energy level, involving the energy. And that's why such absorption of radiation taking place in a ultraviolet or the infrared. And that is why they are not the color, will be colorless. So if we see now the color of the transition metallides, so you can prepare one table. Tripartite lanthanide ions. Then we have the number of 4F electrons. Then we have the color. Then again number of 4F electrons and tripartite lanthanide. So this is the situation in case of the lanthanides. So take the lanthanum 3 plus, cerium 3 plus, praseodymium 3 plus, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, and gadolinium. Now write the other members. So I am writing here now in a reverse order. Gadolinium 3 plus. Then we have the terbium, dysprosium, holmium, then erbium, then thulium, then ytterbium, and then lutetium. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, including lanthanum. Now, how many electrons are there in tripartite lanthanide, not the lanthanide? You have the configuration 4F0. Lanthanum configuration is the 4F0, 5D1, 6F2. That is the in terms of the xenon. Lanthanum has configuration. Lanthanum, not the lanthanum tripartite. When it from the tripartite lanthanide, these 3 electrons will be lost, 2 from the S and the 1 from the V. That leaves the 0 electrons. So lanthanum has the electrons of the 0. So you have 1, 2, 3, 4, 5, 6, 7. Again we have the same situation. We take the reverse forward 7 here, and it will be 7, 6, 5, 4, 3, 2, 1, 0. Now if you see the color of these lanthanides, color is colorless. Color is colorless. It is a green, reddish, pink, yellow, pale pink, and colorless. So colorless, green, reddish, pink, yellow, pale pink, and the colorless. So this is the combinations, or this is the representation of the colors of the all the tripartite lanthanides. Here lanthanides have the 3 plus electrons are the 0. That means your cell is complete. No electrons are present here for but 1, 2, 3, 4, 5, 6, 7, 8. Cell. For lanthanide ions, you have the no electrons, cell you have cut. Same manner, lutetium also you have the no electrons, cell you have cut. And that's why here the transition of the electrons does not take place here, because there will be no electron present in a cellular reactor, and that's why the color of the lanthanide ion is a colorless. That's why at first radiation is taking place not in the visible region, but they are in the invisible region involving high energy. Generally, we have this type of the situation that we have the colorless. The visible region is between the 380 nanometer to 760 nanometer, or 3800 Armstrong to 7600 Armstrong. So this is the visible region where the first radiation taking place. If it is below that and higher that, it is called the invisible, that is ultraviolet or the infrared region, you can see. Now cerium has again 1 electron. Cerium and the ytterbium tripositive if we take, then 1 electron is there. So 1, 2, 3, 4, 5, 6, 7. So you have 1 electron is there. So here also the transition of the electron should possible in same subset. In case of the transition metal ion, the transition taking place in the same DD level, that is called the DD transition. In the same manner here, the transition taking place in a F sub level, that is called the FF transition. But here transition does not taking place in the same substrate level, even though 1 electron is present here in case of the cerium and the ytterbium tripositive. That is why the transition taking place in a higher 4th or 5th quantum level involving high energy. That's why at first radiation taking place in a visible region, invisible region, that is infrared region or the ultraviolet region. This is the situation. And all things, praseodymium and green color, reddish color, pink, yellow, pale pink, all these are the colors. So what is our observation here from this table? If you really carefully see, what is your observation from this table? So we can conclusion from this table is that lanthanum ion with a 0 and lutetium ion with a 0 is colorless. Cerium 3 plus with a 1 electron and ytterbium 3 plus with a 1 electron unpaired, that is a colorless. Praseodymium with a 2 electron, thulium 3 plus with a 2 electron are the green in color. Neodymium 3 plus with a 3 electron and erbium with 3 plus with a 3 electron are reddish in color. Praseodymium 3 plus, promethium 3 plus and the holmium 3 plus with the 4 electron unpaired are pink and the yellow color. Samarium 3 plus and dysprosium 3 plus with a 5 electron unpaired are yellow in color. Europium 3 plus with a 6 and the terbium 3 plus with a 6 are pale pink in color. While the gadolinium with a 7 number of electrons is again colorless. The shell is half filled, stable, and that's why it cannot take place in the absorption radiation. So what we say, the particular color is associated with a particular number of the unpaired electrons. That is our conclusion from this table. For 2 electron unpaired, the specific color is green is there. For 6 electrons unpaired, we have the pale color is there. Or that means all the triprotyl lanthanides can show the color of its cations only, and it cannot be affected by changing the anions or adding the color composition groups. So both the colors, both the state in crystalline, solid state as well as aqueous solution, they can exhibit striking color. So except triprotyl lanthanide, except triple lutetium and tripositive cerium and this greater than 3 plus are the colorless. So this is the table where we can show the conclusion. So it is very interesting to know that a particular color is associated with a particular number of the unpaired electrons. But now if you see the another table, then you can have different situation. The color of the all the tripartite lanthanides which are isoelectronic with the non-tripositive lanthanides. So we have the tripositive ion. You have the tripositive ion, then you have the color on the unpaired electrons. Then we have the color and isoelectron. Isoelectronic non-tripolite. See the situation what will happen here. So lanthanum 3 plus, that is colorless. Lutetium, isoelectron. Europium 3 plus, we have the LP. Then you have the gadolinium, which is the colorless. How many electrons are there unpaired? 0. You have a 6 and 6. And then you have the terbium. There is the last element is the lutetium. Tripositive. It's the same. Now we are going to study the isoelectronic non-tripositive. Isoelectronic in the sense the number of electrons are the same, isoelectron. But it is non-tripositive. It may be the 2 plus or 4. So lanthanide ions we take here. So that's what we have taken the cerium 4 plus. Now lanthanum 3 plus, electron for the 4F0, 5D1, 6F2 lanthanum. And when from the lanthanum 3 plus, it is 4F0. In the same manner, cerium 3 plus of the 4F1, 5D0, 6F2. And when from the cerium 4 plus here, cerium has the 4F1, 5D0, 6F2. So it will be hot. 5D1, 6F2. So we have the cerium will be the 4F0, 5D0, 6F0. So lanthanum and the cerium both are, we can say, isoelectronic here, which contains same number of electrons. How many? 0. But it is observed that, interestingly, the color of the cerium 4 plus here, 4 plus, is orange red. It is orange red. Then European 3 plus, which have the pale pink color, which is equivalent, we can say isoelectronic with the samarium 2 plus. And it is found that the color is reddish. This color is reddish. Samarium. Now gadolinium contains 7 electrons. So here europium 3 plus is there, and if you take the isoelectronic europium 2 plus, then its color will be what? The color will be the straw yellow. So gadolinium 3 plus contains 7 electron unpaired, so it is half paired. And if you take the europium 3 plus, we have the 6 electron. But same europium in a 2 plus state if we take, then one more electron will be added here, that is 7 electrons. Now they are isoelectron, but it is non-tripositive. They are all the tripositive. And lastly, lutetium 3 plus is there, and if you take here the ytterbium, ytterbium will be the 2 plus here contains, non-tripositive. So lutetium has the 7 electrons. Lastly, unpaired electrons are the 7. Then here we have the ytterbium 2 plus 4F13, 5D, 4F14, 30, 06F2, and ytterbium 3 plus is 4F13. Zero. That means 6 electron pair, but ytterbium 2 plus if you take here, ytterbium 2 plus will be the 4F14. So that is the electrons are there, 7 unpaired electrons are there in that case. So how many electrons will be present here? If you see here, ytterbium 2 plus will be the 4F14. That means 4F14, 5D, 0, 6, 8, 0. So all the electrons will be paired here. And that's why same case in lutetium also. Lutetium 3 plus, electrons will be the 0. But all are the colorless. This we have seen. It is colorless. So the color of this ytterbium 2 plus is found to be green. Though they contain same number of electrons, the color is green. They contain same number of electrons. Now I will ask you a question. Earlier we have studied this table, and now we are going to study this table number 2 here. Then what is your conclusion from this table? Lanthanum 3 plus with 0 electron unpaired is colorless, while cerium 4 plus, which is the isoelectronic non-tripositive lanthanides, is orange red in the color. Europium 3 plus with a 6 number of the unpaired electrons is a pale pink, while which is the tripositive lanthanide, but samarium 2 plus, which is the non-tripositive, the dipositive, but it is isoelectronic, containing same number of unpaired electrons, is reddish in color. Gadolinium with the 7 electron unpaired is a colorless, while europium 2 plus with the same number of electrons but dipositive is straw yellow. While lutetium 3 plus with a 0 number of electrons unpaired, all electrons are the paired, then colorless. But ytterbium 2 plus, which contains the same number of electrons, is green in color. So we can say situation is not simple like in table number 1. So we cannot say that particular color is associated with a particular number of the unpaired electrons here. So we can say the color can be more strikingly color obtained when the elements are in anomalous transitive state. So the elements with element valency state +2 and the +4 are more deeply colored than the elements in a normal valency state, that is tripositive state. That is our conclusion. So these are the observation that we cannot say they are deeply. So here in case of the lutetium, ytterbium and the iron rate, this range color which is obtained here, though the electrons are unpure, all the electrons are paired here in cerium because no electrons are there for the transition 1, 2, 3, 4, 5, 6, 7, cerium 4 plus, like in lanthanum plus. So strong color which is obtained in case of this cerium 4 plus is because of, we can say, the configuration changes. See, because of the configuration changes, we cannot say the absorption taking place in the half state. It may be colorless, no inferior. The others can have the absorption in a visible regions, and that's why they are strongly colored. Here also, ytterbium also have the same situation. The ytterbium 2 plus have the green color because of this configuration changes can be taking place in this case. So almost all the lanthanides can exhibit the absorption in a visible region, and most of all the lanthanides are absorbed in the range of the 2000 to 10,000 angstrom, or we can say 200 to 1000 nanometer. All the ions mostly absorbed in this region. The color ions we can show the color. Generally, they can show the color in the visible region in 400 to 800 nanometer, or 400,000 to 8,000 angstrom. In it, they mostly colorless. The other ions are there which can have the absorption radiation, which are invisible. Some can absorb in the ultraviolet, some can absorb in the infrared region, and that's why they are strikingly colored. They are the colorless. The colorless ions can be absorbed in an invisible region, that is ultraviolet and opaque. Cerium 3 plus, which are the also colorless, that can be absorbed in a sometime ultraviolet region or sometime invisible region, we can say infrared. The only positive ions, which is the cerium 4 plus, which is the orange red, is absorbed in blue and the ultraviolet region. So cerium 4 plus is absorbed in a blue and ultraviolet region. So all the colorless ions we can say absorb in a ultraviolet and infrared, and alternatively, or we can say occasionally in infrared region they can be absorbed in ultraviolet region. So this is the color is not a physical or the quality significance. It is just the absorption of the radiation in one region to the another region, from one subset to the other subset. And if the transition is possible, then they can show the color. And if the transition is not possible in the same subcell, they require high energy, and high energy required indicate that they have to absorb in a next quantum level, fourth or fifth quantum levels. Here, porous electrons are deeply buried inside the well, and they are well protected by the pi s and the pi p orbitals. That's why they do not have any effect of the surrounding ligands on this lanthanide ion electron present in the porous shell, and that's why the color of the lanthanum complexes are also generally the current of their color of their parent metal ions, which are the non-affected. Just have told previously, they are unaffected by the anions or the identical complexing group. So this is the lanthanide ion and their significance color in a different properties. So this completes the color property. Now the next property is that is of effervescent spectra. Again, it is based upon the same concept of the color. So, effervescent spectra. It is a very small property as compared to the others. So, effervescent spectra of the lanthanide ions, all the tripartite lanthanide ions is carried out. We found that they can show the sharp line and line-like spectra, except the lanthanum 3 plus, lutetium 3 plus, and the cerium 3 plus, ytterbium 3 plus. Generally, except this element, all these lanthanide can show the sharp line and line-like spectra of the lanthanide ions. Now, these spectra cannot be affected again by the nature of the anions. When they change the spectra, the general spectrum cannot be changed. General spectrum remains the same. Just the wavelength can be changed. That is why some of the lanthanide like lutetium or tripartite lanthanum or cerium 3 plus or ytterbium 3 plus, these can show the broad efflorescent bands here. So these the broad efflorescent bands are there, like in case of the transition metal ions. In transition metal ions, what happens? The electrons which are present that are in the outer shell, these are the n-1d electrons which are incompletely filled and they are in the outer shell. That's a surrounding leakage. Environmental factors can affect these outer electrons. And that is why in transition metal ion, the bands which are obtained, that first bands are there, that effervescent spectra is broad bands like that, broad bands. But in case of the lanthanides, the electrons that are responsible for this effervescent spectra, again, these are the n-2f, that is the electrons, and they are well protected by the phi s and the phi p or the phi d orbitals, or 6s orbital. And that's why the environmental factor does not have any effect on these properties. That is why they are well protected and they can show the effervescent bands here, which are the sharp. So these are resembling the lines of the emission spectrum. So whatever effervescent bonds we obtain, that is sharp. And that sharp bands is like the lines of the emission spectra. So here we have this effervescent coefficient 0.02, 0.04, 0.06, 0.08, 0.02, 0.08, 0.06, 0.04, 0.02. If we brought this spectra here, then somewhere here 3318, 4200, 4400, 4600, like that, 500. The wavelength of the effervescent 4400. So when this spectra is carried out, it shows generally in case of the broad specific sharp line like spectra. Sharp line spectra is obtained here in this case, in case of the praseodymium chloride. While if you take another spectra of the neodymium, here we can get this type of the nature can be observed here. This is the neodymium chloride I am getting here. So sharp line or line spectra is obtained in case of the lanthanides here, in case of the neodymium and the which contain the unpaired electrons are there and transition can be easily possible. But if the broad bands are obtained, then the broad bands can be converted into sharp bands. The conversion of the broad bands into the sharp bands can be possible by just lowering the temperature or cooling the spectrum. Lowering the temperature, so general spectrum cannot be changed here. We can just convert, we can just transform this wavelength of the F here, and broad band can be changed to the converter. So on the other hand, the broad bands which are obtained in case of the lanthanum or the cerium 3+ or the yttrium 3+, that can be changed to the sharp bands by changing the frequency. So at first spectra of the lanthanum complex can reflect the energy changes from the various energy states, and under this term, they can split into the different spectroscopic states. They can withhold into the spectroscopic states, and therefore they can show the broad effluxing bands here. Broad effluxing band can convert into the very sharp bands. That is possible. So the broad bands which can obtain here in case of the cerium. So cerium will be there. This type of broad band will be there. In that broad band, because of the configurational changes, we can see. And just doing the third property also. The broad bands which are obtained. This is the. So this can be the effluxing spectra of the complexes.